Hey everybody, this is Chris Dingman, the Math and Science Explainerator and a private online tutor. I'll give you my website in a second here on the screen. This video covers the X-Intercept form of quadratic functions, otherwise known as factored form. And you can watch this video on its own, but it's also the fourth video in my series on quadratic functions and parabolas. So if you want to watch the series in order, which I recommend, the video to watch before this one is about standard form of quadratic functions. All right, so we've been talking about quadratic equations, and we've been talking about how a parabola is like a visual representation of a quadratic equation. And we've been talking specifically about two forms so far of a quadratic equation. And they are the vertex form up here and then the standard form down here. And I showed you in the video on standard form how you can start with a quadratic in vertex form and transform it magically, or not so magically, into a quadratic in standard form. So I'm going to write another quadratic in vertex form here. And now I'm going to quickly transform that into standard form. And if any of that didn't make sense, you can go back and have a look at the video on standard form, or just pause the video and have a look a little more closely. Otherwise, I'm going to erase them now and move this equation under this one. All right, and now let's relate this visually to a parabola. And remember, I could also call y f of x. You're often going to see it that way, and it's probably better. I should probably do that more often here. So parabolas are U-shaped things, and that's what the graph of these quadratics look like. And then we were talking about, well, what can you tell about a parabola from looking at the equations? And we found that when a quadratic's in vertex form, you can read the, wait for it, vertex. And that vertex is hk, xy values, in this case 1, -16. You can also read up, down, wide, narrow from this a value out front. All right, jumping down to the standard form, we learned that you've still got that a value out front, same thing, same number, same indication, up, down, wide, narrow. And we also found that the standard form is nice for telling you the y-intercept of a quadratic. In this case, it's -12. It's that c value hanging off the end. Now, of course, if you wanted to know what any graph of any function looked like, I'm going to emphasize this over and over, you would make a table of values. You would plug in a bunch of x values. You would get a bunch of y value outputs, and I'll just make some up here. You would plot those points, and you would plot as many as you felt like or had time for. If you were super bored, you'd get a lot of points, and they'd all smear together into what we call the graph of that equation. So that's always an option, but we like easy things. We like to be able to look at these equations and get some information and get an idea of what the graph's going to look like. So 1, -16, I'll make 1 right here, and I'll make -16 down here. Without plotting a darn thing, we know that's the vertex of our parabola from our vertex form. And we know -12 is the y-intercept from our standard form. So let's say that's about right here. And then both forms with this 4 tell us that our parabola is going to be facing up because 4 is positive and narrow because it's bigger than 1. So I'll just sketch that in. We also talked about something called the axis of symmetry, which is just a line that splits the parabola in half. It's always a vertical line. It always goes through the vertex, and its equation is always x equals the x-coordinate of the vertex. So let me write the coordinates here. So here's the axis of symmetry, and its equation is x equals 1 in this case. And remember, we could get that x equals 1 either from the vertex form or the standard form. The vertex form is easier because it's right there. It's just the opposite of that number. In the standard form, we had to use a little formula, and that was this. It's the opposite of the b value over 2 times the a value. So with this quadratic in standard form, we would have x equals the opposite of negative 8, so that's just positive 8, over 2 times 4. So x equals 8 over 8, which is 1. So we get that 1 that way as well. So we've talked about some key features of parabolas so far. We've talked about, are they facing up or down? Are they narrow or wide? Where's their axis of symmetry? Where's their vertex? And where's their y-intercept? And the last two, the vertex and the y-intercept, are points, right? There's 2 more points, and you might see them here, that are important for parabolas. The prestige points. And let me put little arrows here. Forgot to do that. Graph goes on forever after all. Okay, do you see our important points, our 2 other important points? They're the x-intercepts. So that point and that point, right? If I had the vertex, the y-intercept, and the 2 x-intercepts, those are really good anchor points to give me an idea of what the parabola is going to look like. So how do we get those x-intercepts? Well, do you remember how we got the y-intercepts? To get the y-intercept, we plugged in 0 for x. So let me clear some space here. And it's really important that you remember why we did that. Okay, here's the y-intercept. What are the coordinates of that y-intercept? They are 0, negative 12. That's the reason we put in a 0 for x to find the y-intercept, because that first number, 0, represents an input, right? And that second number, negative 12 in this case, indicates the output at that input. And any y-intercept, right? I could draw any insane graph I felt like. So let's say that. Any y-intercept, right, it would be like right there, is going to have an x-coordinate of 0, right? Because you go 0 on the x-axis and then up, let's just say that's an 8. So that would be 0, 8. Any y-intercept for any graph will be the y output when x is 0. So you never need to be mystified in math ever again for any question about what's the y-intercept for this function. Put in 0 for x, period. But now we're looking for the x-intercepts. Well, it's the same logic, because what are the coordinates for any x-intercept for any function in the world or on any other planet? Well, let's draw a random function here, because this logic is going to be true again for any function. Here's a random function going along. Here's an x-intercept. Well, let's just pretend that's 5 on the x-axis. What are the coordinates of that point? 5, 0. So notice, well, let's do another one. Let's go back here. Here's another x-intercept. Let's say that's at negative 3. So we're going back 3 on the x, 0 on the y, 0 on the y. I'm saying that because you put in 0 for y, and that will give you the x-intercept. We put in 0 for x when we wanted the y-intercept. Those are really key things to remember. Now, you may or may not have perked your ears up there when I said you input a 0 for y to find the x-intercepts, because we've been talking about x as the input so far. But you may know that you can actually input something for y and output something for x. So you can think of either variable as the input or the output. It's just easier when you think of x as the input because all the x's are over here, and it's easier to plug in something for x and get out something for y. But it works both ways. So like for this parabola, I could plug in, let's say, a 2, and what's the output? Well, it's wherever the 2 hits the graph. So you come down to this point, then you bounce on over here, and maybe it's something like negative 10. Okay? But what if I decided to input for the y value? Let's say I decided to input a negative 2. Now, notice I actually have two, if we think of them as outputs for x. I'd bounce over here to, let's say it's -1, or I'd come over here and hit the graph at, let's call that 2.5 or something. So the point is, I can input something for y and see what I get out for x. So to find my x-intercepts, I'm just going to input 0 for y and then see what I get for x. So let's do that over here. In place of y, I'm just going to put a 0. Now, that's a little harder to figure out than just putting in a 0 for x and figuring out what y is. Remember, when we put a 0 in for x to get the y-intercept, these terms just went bye-bye and we got -12 easy. But now when we put in a 0 for y, we're saying, well, what number squared times 4 minus 8 times the same number minus 12 will give me 0? That's not obvious. How about in the vertex form? How easy is it in that form? Let's try it. I'm going to put 0 in for y and see if I can figure out what x is. I'm going to add a 16 to both sides. Now I'm going to divide both sides by 4. Now I'm going to square root both sides. Now here we have to be careful on the left with the square root of 4. You might think it's a simple 2, and you'd be half right. Because another thing that you can square to get 4 is -2, right? -2 times -2 is also 4. So anytime you square root both sides of an equation, you've got to slap a little plus minus in front of that square root on one side, and that's going to cover both those options. So let's proceed. On the left, we have the square root of 4 is 2, but we need the plus and the minus, so plus minus 2. And on the right, a square root just undoes a square. So the square root of anything squared is just the anything. And the anything in this case is x minus 1. Hope that made sense. Now, x minus 1 equals plus or minus 2. So I'm going to add a 1 to both sides, and now I've got 1 plus or minus 2. This is the one I added. So that's actually two answers. X is 1 plus 2, which is 3, or x is 1 minus 2, which is -1. So that wasn't too bad. I mean, I don't know what you thought, but but just to recap, we wanted the x-intercepts, so we put in 0 for y. We put that 0 in for y in the vertex form, and then we solved for the x values, and we got 2 of them, which is what we were expecting, right? We got one here at 3 and one back at -1. Notice that 3 and -1, those x-intercepts, which are important points for a parabola, you don't see them anywhere here in the vertex form. Nor do you see them over here in the standard form. We don't see 3 or -1. There is a form, though, where you can see the x-intercepts right in the equation, and that's what we're going to talk about now. All right, so I'm going to make some space here. Getting to intercept form for a quadratic requires doing something called factoring. Factoring is just writing a number as two numbers multiplied together. We're all used to seeing, for instance, a 12 is 3 times 4. I just factored the 12. Wherever I see a 12, I can substitute 3 times 4. I wrote it as the product multiplying of two numbers. Why would we do that? Well, here's why we do that. It makes solving this equation easier. And it makes it easier to solve because if two things multiply to equal 0, let's just call them a and b, okay? So a times b equals 0. Don't we know that either a has to equal 0 or b has to equal 0? The only way to multiply two things and get 0 is to have one of them or both of them be 0. That's why if we can write this thing as something times something, in other words, if we can factor it, we can make our life easier because we're going to have hopefully two nice, simple little equations. Now you might be thinking, I understand factoring 12, that's 3 times 4, I'm factoring a number. How are we going to factor a whole quadratic? Well, let's see how that works. And to look at how that works, we're going to start with a quadratic in factored form and bring it up to standard form. So I'm going to go through a process and then we're going to learn how to go in reverse. Don't worry, this will all make perfect sense. Say I had x plus 3 times x plus 5. That is in the form of a times b. It's just that a is this whole thing and b is this whole thing. So that's the form we're looking for. That's the factored form. Now, if we FOIL that out, remember foiling. If you don't remember foiling, look at the last video on standard form. We would get x squared plus 5x plus 3x plus 15. And then we'd get x squared plus 8x plus 15. So this is in standard form, right? So to factor a quadratic, we're just going to take it from this back to this. So that's something that might take a little practice, but you'll get the hang of it. And that will help us write this standard form of a quadratic in factored form. And then that's going to make things easier to solve, because say this was equal to 0. There's my y value that we set to 0 to find the x-intercepts. If I could rewrite it back this way so that that equals 0, now I can say that this is a and this is b, so either a equals 0 or b equals 0. And look how simple that is. If x plus 3 equals 0, subtract a 3 from both sides, and I get x equals negative 3. And then down here, I just subtract a 5 from both sides, x equals negative 5. So I have solved for x, even though if I was given it in this equation, it's not obvious that negative 3 and negative 5 are there. But notice that the 3 and the 5 do show up in the factored form. You can see them right there, although you can see their opposites right there. Just like in vertex form, you saw the opposite of the x-coordinate of the vertex. So now our job is to take this orange quadratic and factor it so that we can find the x-intercepts. Well, how are we going to do that? Factoring is just a skill. You get better at it with practice. You may take to it quickly. You may want to take a little more time to practice. But how do we go back from this form back to this factored form? Well, notice that this first term x squared came from multiplying the first terms in these two binomials, x times x. So that's a first in the foiling, right? Remember, first, outside, inside, last. We talked about foiling in a previous parabola video. And notice that the last term right here comes from multiplying the last terms in the binomials. 3 times 5 is 15. Now the middle term comes actually from the multiplying the outside and the inside terms in the original. So that's outside, there's the outside, and the inside, right? 5x plus 3x. And then those combine to make the 8x. So it boils down to this, at least when there's a 1 in front of the x squared, so it's just going to look like x squared. It boils down to writing two parentheses and making sure that this times this gives me that, and that this times this gives me that, and that this plus this gives me this. So I started with a pretty straightforward one, and notice, of course, that that's the factored form. So let's see if we can do that with our orange parabola. Now, I'm not going to go in a lot of practice with factoring in this particular video. I'll probably do a video on more factoring and getting into it in more detail, or you can look at some other practice online for that. Right now, I just want to focus on why factoring is useful for working with quadratics and parabolas. So let's try to factor this orange thing. And no, orange thing is not a technical math term. Now, the orange thing is different from the yellow thing because, well, the numbers are different, of course, but we can actually factor something out of all the terms here in this orange quadratic. And that's actually the first thing you always want to do. You want to see if you can factor out something from all three terms. In this case, you can because a 4 goes into all three terms. So we could write that quadratic as this. That's good because it gets the numbers down in the quadratic that we have to factor. We only have to factor this now. The 4 can just stay sitting outside. So we're going to factor this quadratic. Okay, this times this has to give me the x squared. All right, that's straightforward. All right, and then these two numbers in these slots have to multiply to -3, and they have to add to -2. Well, let's see. -3 times +1 does multiply to -3, and that adds to -2x. In other words, if I FOILed this out, it would give me this. So I have factored my standard form, and I have now written this quadratic in what we call X-Intercept form. Because remember, when I have things multiplying together to equal 0, that's this a times b equals 0, over here, I actually have three things multiplying to 0, but the concept remains the same. I have a 4, an x minus 3, and an x plus 1. So if any of those things equaled 0, then this whole thing would equal 0, and we'd solve the equation. So can 4 equal 0? Well, I don't think so because it's a 4. That's why we call 4 is a constant. It's constantly 4. It doesn't say today I feel like being 0. However, the next two things have variables in them. They can vary. So x minus 3 could equal 0. Add a 3 to both sides, and we get x equals 3. Or, big fat or, x plus 1 could equal 0. In which case, x equals -1. So those are our x-intercepts, because that's where y equals 0. And you can see that they make sense with this parabola from what we already knew about its vertex and facing up and all that good stuff. We have our -1 x-intercept over here and our 3 x-intercept over here. All right, let's move some things around. So this is an example of x-intercept form, and now I'm going to write the general x-intercept form. So once again, this x-intercept form, or factored form, really you could call them either one, is really nice in order to find the x-intercepts, because the x-intercepts are where y equals 0, and once we make y equal to 0, it's nice to be able to write the other side as something times something, so that we could say, okay, either this thing is 0 or this thing is 0. All right, so let's put this thing in a green oval. So when you have a quadratic in x-intercept form, what's often called the p and the q are the x-intercepts. And notice there's a minus sign in front of both, just like there was a minus sign in front of the h in vertex form. That's telling you that when you look at an equation that's in factored form, like this up here, or x-intercept form, the x-intercepts are going to be the opposite of the numbers you're looking at. So we see a -3 here, but we saw that the x-intercept was a +3. We see a +1 here, and we see that the x-intercept was a -1. So it's the same concept that we talked about over in vertex form. And just to show you that, I'm going to rewrite this example so there are minus signs in both of the factors. I'm going to change this 0 back to a y. Remember, we substituted 0 for y so that we have an equation. And if I were to write this in factored form, this would still be minus 3. But this would be, we need a negative sign. We need a subtraction to technically have this in X-intercept form. So we see a plus 1. We're going to make that a subtracting a negative 1. Same thing, right? So notice now we have it exactly in the X-intercept form, and we can see that P is the number after the negative sign, in this case 3, positive 3. Q is also the number after the negative sign, negative 1. Okay, but again, you can, if you don't want to worry about this down here, the X-intercepts are the opposites of the numbers you see here in the factors. Now, also notice that the X-intercept form keeps that same A we keep seeing in all the other forms, right? That A out front is the same A in vertex form. It's the same A in standard form. So all three of these forms have an A value, which will always stay the same, and always tell you whether it's facing up, down, wide, or narrow. So that's like the constant thing that all three of these show you. But that's the only thing that they all three show you, at least directly, right? All right, let's do another example. But first, let's add our factored or X-intercept form to the list of forms. We'll do another example, and this time we're going to start with something in standard form. This time I'm going to write the function with f of x notation. Instead of using a y, I'm going to say f of x equals x squared minus 5x minus 14. Okay, it's in standard form. We know that our a value is that mysterious invisible 1 there, so a is 1. And the y-intercept is negative 14, right? That's that c value. So that's some information. Let's see if we can find the x-intercepts. X-intercepts are where y, or f of x, equals 0. So we're going to replace this with a 0. Now, that's not easy to solve. Something squared minus 5 times something minus 14 is 0. But if we factor it, we can do it. So, what's the first thing we do when we factor something? Remember, we said we look to see if there's something that every term has in common that we can factor out. But these don't. Nothing goes into 1, negative 5, and 14. So we can just go right to the 2 parentheses factoring. And this is going to factor like this. Right? So x times x is the x squared. Negative 7 times 2 is the negative 14. And then the outside and the inside is going to be the 2x minus the 7x, which is negative 5x, and that gives us the middle term. So I was just showing you that I factored it correctly. Hope you're proud of me. And now let's look at why we did that. When we're adding up things to get 0, it's tricky. But if we multiply two things to get 0, we know that one of those two things has to be 0. That's why we factored this. So either x minus 7 equals 0, or x plus 2 equals 0. Now we have two simple equations, x equals 7, or x equals negative 2. So this parabola, we already knew it has an a value of 1. And by the way, that a value is still right there. There's a 1 outside those two parentheses. This parabola has an a value of 1. It's facing up, and it's kind of medium width. It has a y-intercept of negative 14. We knew that. So let's start graphing it. Y-intercept negative 14. Put that down here. Let's say that's negative 14. And we know it's medium width and it's facing up. So it's hard to know what it looks like so far. But we also have the x-intercepts of 7 and negative 2. So 7, negative 2. So now we can sketch at least a decent idea of what this thing looks like. Let me try that. So notice I kind of approximated where the vertex might be about. It's right about there. And that's pretty good. Now, remember, we could find the x-coordinate of the vertex using the formula negative b over 2a that's based on the standard form. But there's actually another way to find it, because parabolas are symmetrical. So those two x-intercepts, negative 2 and 7, have to be symmetrically arranged around the midline or axis of symmetry of this parabola, right? There's the axis of symmetry. And, well, what number is halfway between negative 2 and 7? One way to do that is just say what's the average of negative 2 and 7. So all we'd have to do is add them up and divide by 2. So the axis of symmetry is goes through 2.5, so it's x equals 2.5. And that's also the x-coordinate of the vertex. How would we find the y-coordinate? That's right, just plug it in to the equation and you'd find the y-coordinate. But I don't feel like squaring 2.5, so I'm not going to do that. But I will show you that we get the same thing using this negative b over 2a, right? Negative b over 2a, based on the standard formula, I should say the opposite of b over 2a. b is negative 5, so the opposite of negative 5 over 2a is 1, equals 5 over 2, which agrees with what we got using this technique of just going right in between the two x-intercepts. So that is x-intercept or factored form of a quadratic, and that completes our overview of quadratics and parabolas and the three forms that you could see them in, and what you can tell about the parabola by looking at the numbers in these different forms. All right, that's the last video in my quadratics and parabolas series. If you're interested in private online tutoring in math and science, contact me at my website, and I'll see you in the next video.